Okay, so welcome everybody for our last section of this semester. So today we are going to, Karina Marin from Federal University of Rio de Janeiro is going to speak about continuity of center-Lyapunov exponents. Please, Karina.
Okay. Thank you, Lucas. Just let me, sorry. No, okay, thank you. So first I want to thank Lorenzo for the invitation. It's very good to be able to speak at Resistencia Dinámica. And as Lucas mentioned, I'm going to discuss about continuity of center-Lyapunov exponents. Sorry. And so this center is here because I'm going to deal with partially hyperbolic diffeomorphisms. So M is always going to be a compact connected manifold. I'm going to take C2. All the things that I'm going to talk today are true for CR with R greater or equal than 2, but in order to simplify the notation, I'm going to fix C2. And I'm going to study partially hyperbolic diffeomorphisms. So as you know, for partially hyperbolic diffeomorphisms, I have a splitting of the tangent bundle in 3 different subbundles that I'm denoting ES, EC, and EU. All of them are invariant for the derivative of the map F. And what I have is the derivative here contracts the vectors, here expands, and the behavior here is dominated by the behavior in ES and EU. What this means is if I have a contraction here, it's not going to be as stronger as the contraction here. If I have an expansion here, it's not going to be as stronger as the expansion here. Okay. But it could be that I have neither of them. So in general, I do not have much information about what happened in the center band. So the tool that I'm going to use to study the dynamic of the center bundle is the Lyapunov exponent. So I'm going to fix an ergodic measure. And from now on, my measures are always going to be ergodic. If I forget to mention, the measure is always ergodic. And here I'm denoting by C the dimension of the center bundle. And what Ocellet's theorem says is that I have C numbers that I'm denoting this way is with what I call center Lyapunov exponent. And these numbers here are giving information about the asymptotic behavior of this subbundle EC. I'm not being very precise about this definition now, but in a minute, I'm going to fix in a simpler case, and I'm going to give you the definition of the Lyapunov exponent. What is important here is that give me information about what happened with the dynamic in the center. So one important definition here is the following. In my particular context, I'm going to say that a measure is hyperbolic if all these numbers are non-zero. This is important because it gives me direction with non-uniform contraction and direction with non-uniform expansion inside of this subbundle. And I have several tools to study the dynamic when I have a measure that is hyperbolic. So finding conditions for a measure to be hyperbolic is a very difficult problem. It's a completely different problem from which I'm going to talk today. Today, what I want to say is something about the continuity of these numbers. So to be more precise, the question that I am interested in is this. So I'm going to consider here a diffeo, and my diffeo is always partially hyperbolic. I'm always taking it C2. I'm perturbing the C2 topology, and my measures are always ergodic. And I want to know how these numbers are changing when I perturb my diffeo and my measure. In a very good situation, this should be a continuous function. So why this is important? Because if I'm able to prove that the measure is hyperbolic, some property like this, some positive answer to this question is going to give me that the Lyapunov exponent for the perturbed system are also non-zero, and this gives me good properties for the perturbed diffeomorphisms. So this is the general question that I want to address today. It's a very general question, so I'm going to start to restrict myself to simpler cases. I want to start by observing that the first case, the easy case, that is when you have the center dimension equal to 1. We already know that this is a positive answer. This map is continuous when the center dimension is 1. This is because we have that domination between the three bundles that I mentioned at the beginning. So the second most easier case that we can think of is taking dimension 2 in the center bundle. So from now on, I'm going to focus in partially hyperbolic diffeomorphism that have center dimension equal to 2. And in this particular case, I can give you a precise definition of the Lyapunov exponent, that is this here. So recall that my measure is ergodic, and what Lyapunov exponents are doing here is, as I mentioned before, given information about the asymptotic behavior of the differential map restricted to the center bundle. So observe that here, in this one, I take in the norm of the n iterate of my derivative, and in this one, I'm taking the co-norm. So these two numbers are going to give me information about the behavior of the derivative restricted to the center bundle. And just to be clear, the question that I'm going to try to answer is if this function here is continuous or not. And since I'm restricting myself to center dimension 2, I'm going to have to work only with two different, not necessarily different, with two numbers that are given by the center Lyapunov exponent. Of course, the question makes sense perturbing the diffeo and the measure. Most of the talk, I'm going to consider this measure fixed. Perturbing the diffeo and perturbing the measure are two different problems. Usually, if you put a good measure, for example, you fix Lebesgue measure, then you have very good properties to deal with perturbing the diffeo. So this is essentially what I'm looking for, fixing the measure here. So there are a lot of tools and approach that you can choose to address this problem. What I want to present today is using linear cocycles. So linear cocycle has been studied for several years now. You can define them in very different contexts, and it has several applications, not only in mathematics and physics and in other areas. But for the purpose of this talk, I'm thinking of linear cocycles and an easier model, a simpler case for the case that I want to study. So I'm going to restrict myself to the settings that can give me information about this problem of center Lyapunov exponent for partially hyperbolic diffeomorphism. So what I understand for a linear cocycle. So a linear cocycle, it's going to be defined by two elements. The first one is this here. It's a vector bundle. I'm taking the fiber to have dimension 2 because I fix the center dimension equal 2, and I'm going to take the derivative as an example of this linear cocycle. So I'm going to restrict to dimension 2. Moreover, the results that I want to study for continuity of Lyapunov exponent are most known for dimension 2. So I'm going to restrict to dimension 2. This is a vector bundle, and I have a map that I'm denoting F here that is continuous. I'm asking for this diagram to commute. And I have that the action of F in the fibers is given by linear isomorphisms for every sheath. Okay. And as before, I'm fixing in the baseline measure that is ergodic. So it is clear that the first example that you can think about this is which I'm calling here center derivative cocycle. So what I'm doing is I'm taking the center bundle that I fix as two-dimensional, and it is very easy to see that I can define this linear cocycle that is just the derivative of the map restricted to the center bundle. So this map is a particular case of a linear cocycle. And as before, when I studied the Lyapunov exponent of this map, if you recall, I was studying the norm and the conorm of the iterates of this map. I'm going to return here. So this was my definition in dimension 2 for the Lyapunov exponent. It is clear that I can put here the norm of the cocycle and the conorm of the cocycle, and I will get again Lyapunov exponent that now are Lyapunov exponent for a linear cocycle. So I can restate this question to the setting of linear cocycles. This is what I did here. Oh, I know that it was going to happen. Sorry. So here. So in this setting, F is a linear cocycle. I'm dealing with a vector bundle of 2 dimensions. And I can ask about what happened with this function. This is analogous function to the function that I was thinking before. There is a difference here that is very important. That is that in this second question, my base F is fixed and my vector bundle is fixed. I'm only perturbing my map F. When I'm studying the center Lyapunov exponent of a partial hyperbolic map, I'm doing this for this map. So when I perturb my map, I actually perturbing the base, and I'm also perturbing the vector bundle here, because all of this is changing when I change my DFF. So this is not exactly the same question as before. Giving an answer for this question is not going directly solve the problem of the center Lyapunov exponent, but it can provide tools and can give evidence of what happened and what can we expect for the center derivative cocycle. So my objective is try to understand this question to find things that give me some ideas of what to do in the case of the center derivative cocycle. So, sorry. What I want to do is to study this question. And most of the, all the theorems that I'm going to state today are going to use the notion of fiber bunch cocycles. So in order to study this question, most of the things that we know for fiber bunch cocycles. So I want to explain to you what fiber bunch cocycles means. So I just define a fiber linear cocycle is this map F. I know that in the first coordinate, it acts by my base F, and here I have a linear isomorphism. And I want to define this notion of fiber bunch. So for that, I'm going to define a new cocycle that is not going to be a linear cocycle now, but it's a projectivization of this linear cocycle. So what I'm doing here is I'm considering a new map that is defined in this fiber bundle. Now the fibers are circles. Remember that here the fibers were vector spaces of dimension 2, and I'm taking the projectivization of these fibers. So I'm going to obtain now a fiber bundle that has circles in the fibers. And the map is just defined by taking the corresponding class here. For every map, for every point she's B, I'm going to take the base map F in the first coordinate, and I'm going to take the class of the linear isomorphism that I have defined here. So now this map is a fiber bundle by circles, and this map is acting in the fibers by diffeomorphisms given for this. And I'm going to say then that my linear cocycle is fiber bunched if this new map here is partially hyperbolic. So what does this mean? I fix at the beginning F as being partially hyperbolic, but the definition is the same if you put an another here. The important thing is that you need to have some contraction and some expansion in the base. And what this condition means is that the action in the fibers is dominated by the contraction and the expansion in the base. Okay. So I don't know what happened in the fibers, but as before in the definition of partial hyperbolicity, I'm asking for the contraction and expansion in the base to be stronger. And why this is important? This is important because it allows us to define a stable and unstable manifolds for this new map. So here I have a picture. This is a stable manifold in the base. These circles are my fibers over G's and over epsilon. And for every point B here, I know that is going to exist a stable manifold that is a stable manifold for this map for the projectivization. Moreover, this is a graph over the stable manifold of my map F. And I have a similar picture when I look to the unstable manifold. And this is going to allow me to define holonomies in the usual way. Given two fibers here, I'm going to define a stable holonomy just as intersection with the fiber of this stable manifold. And in the same way, I'm going to define an unstable manifold between 2 points in the same unstable leaf. So what is important when I'm saying that my cocycle is a fiber bunched cocycle is that I'm able to find holonomies between every 2 points in the same stable or unstable manifold. And this is important because I have a relation here. It is possible to prove that you have a relation between the Lyapunov exponent that I'm interested to study, the Lyapunov exponent of the linear cocycle, and the measures that are invariant for the projectivization. So if come back here, I'm studying the Lyapunov exponent of this map, but there is a relation between this Lyapunov exponent and the measures that are invariant for this map. This is a result of Ledrapierre. And then if I take any measure here, I'm going to call M. I can take the disintegration of this measure along the fibers, and it's going to give me here the element in sheath and here the element in epsilon. And these holonomies can give me information about what happened. For example, you can ask if you take this measure by the holonomy, if it's going to coincide with this one or not. So the general idea behind proving continuity using fiber bunches is that you have a relation between Lyapunov exponent and invariant measure for the projectivization. So you use the holonomies to get properties about the measure in order to conclude the properties that you want for the Lyapunov exponent. So these holonomies are going to give you what you need to get the continuity of the Lyapunov exponent. And they have a very important property that I'm going to write here. Fiber branch is open. So if I have a linear cocycle that is close to my fiber branch cocycle, it's going to be also fiber branched. By the definition, it's clear that for linear cocycles that are close, we have holonomies that are close. And moreover, this is true when you consider the center derivative cocycle. So even in the case that we're changing the base, we are changing here the stable manifold, we're changing the fibers, but everything remains close. So this is a very strong property that you can use in order to conclude continuity of Lyapunov exponent. And you are going to see that all the results that I'm going to state require this fiber branch condition. So just to summarize, I'm fixing a measure because I said that I'm going to choose a measure that has good properties, and I'm going to perturb the differ. So I have these two questions. The first one is for linear cocycles. I have the two Lyapunov exponent of the center cocycles, and I would like to know if this is continuous. And the second question is a more difficult question, is the case when I perturb the base and I study the center Lyapunov exponent. As I mentioned, question 1 is not going to imply immediately question 2, but can give you information of what can you expect about the problem. So what do we know about question 1? So I'm going to state the most general theorem that we know so far.
Karina, you said that the question 1 give you some information for question 2. If it's not continuous, can you affirm that it's not continuous in the second case? Something like this?
The problem is the next theorem says that everyone is continuous in question 1.
Okay, so let's wait for the next theorem.
Okay.
Thank you.
But, okay, so answering the question of Jackie, this one was saying that I'm going to perturb only the cocycle. So I'm going to return here to give you a better picture of the problem. So I am here. So maybe when this is fixed and I'm allowing to perturb this, it's very different the situation that I perturbing here. So it is, I think that it works in both directions. So when I have perturbation here, I have much more perturbation than here. Here, a perturbation here changed everything. So I don't think that is a direct relation, but I personally see this as an easier model to understand what happened here. And it's in that sense that I write here these two questions. Sorry. About the linear cocycles first, and about the center Lyapunov exponent of the partially hyperbolic map second. So this here is the most general theorem that we know about linear cocycles. There is a whole theory of linear cocycles. All the results for linear cocycles are actually using things that were proved many years before for Furstenberg and Lederapierre. Unfortunately, I'm not able to give a precise reference of everything, so I choose to explain the hypothesis of this theorem that is the closer one to the things that I'm trying to study when I study the center Lyapunov exponent of the derivative cocycle. So this result is for linear cocycle. So my base is going to be fixed. and it's not partially parabolic, I need a little more. I'm going to ask for it to be anosov. My linear cocycle, I'm going to ask to be Helder continuous, and I'm going to ask this notion of fiber bunch that just tell you about. My measure, as before, is going to be ergodic, and I'm going to need these two red conditions that said that I need local product structure, and my measure needs to have full support. And then in this setting, there is a result of Backes, Brown, and Butler that says that the answer to the first question is yes. If you have this, you can perturb your linear cocycle, and you are going to have continuity of the Lyapunov exponent. I should mention that Backes, Brown, and Butler is a more general result. I choose to present to you the version that is more direct to adapt to the setting of center derivative cocycle. This condition here, fiber bunched, I explained to you why it's useful. These red conditions here are here because in a moment during the proof, you need to do some Hopf argument. You have some property in one point, and you need to take that same property to every other point in your manifold. So you achieve that having full support and having local product structure of your measure.
Sorry, Karina, this is in any dimension or two dimension two or the
dimension two? The diffuse, the base is any dimension. The cocycle has dimension 2.
Okay, thank you.
I'm always fixing dimension 2. In fact, this result is not known in higher dimension.
Okay, oh, thank you.
So here, maybe it would be useful to put that here, but the linear cocycle is 2-dimensional. I'm asking for the linear cocycle to be Helder and fiber bunched, and I'm asking for the measure a little bit more of being ergodic. I have this local product structure and its full support in order to be able to repeat that type of Hopf argument. So if I want to use this to give an answer of question 2, I will have to reproduce this type of condition that are appearing here. So I'm going to define a subset that I'm going to call B, that is formed for partially parabolic diffuse, C2 diffuse. That was my original setting. I'm going to ask for center dimension equal to 2. Again, I was fixing this at the beginning. The fiber bunched here, I will need to ask. I have my center derivative cocycle. This is always Helder continuous. And I'm going to ask for it to be fiber bunched. Recall that fiber bunched means that the action in the fibers is dominated by the contraction and expansion in the base. So this condition here actually implies what is known as center bunched. Okay? And what is important here are these two red conditions, because I told you that I'm using them in order to have this Hopf argument. I have this property in one point and I want to take it everywhere in the manifold. And when your diffuse is partially parabolic, we may know some other types, but the more easy thing to deal with is accessibility and your measure being Lebesgue. So I'm adding here in this setting that was my original setting, the property of accessibility, and I'm restricting myself to the fact of my measure being Lebesgue. And these two red conditions are here in order to replace this condition in the Anosov case. And since this here implies center bunched, but the theorem of Burns-Wilkinson, we know that Lebesgue is ergodic. So I am in the original setting when my measure was ergodic. So what I have done so far is I have this question about the continuity of the center Lyapunov exponent. I'm using linear cocycles to understand better of what happened. So I'm adding information to my original setting of partial hyperbolicity in order to have hypotheses that are similar to the one in this result where I have a positive answer. So I didn't mention, but this set B that I define here with all these hypotheses here is C2 open and non-empty. So this is important information. This is open because I have partial hyperbolicity that is open. The center dimension is going to remain 2. This is a center bunching condition that is also C1 open. And by a result of Avila and Viana, we know if the dimension of the center is 2, then accessibility is an open condition. So all these conditions are open, and moreover, we are able to find diffeos that verify all of these hypotheses. So if I'm using the same hypothesis that here, my conjecture is that probably I'm able to prove also a continuity of the center Lyapunov exponent in this setting. So this would be what we were able to prove in a perfect world. There is some problems in the arguments of the paper of Backes, Brown, and Butler that we are not able to adapt to the partial hyperbolic setting. So I'm going to mention 2 main problems. Of course, this is not everything that is happening in this paper. This paper is very delicate. They use some energy argument that was introduced by Avila, Eskin, and Viana in order to start continuity of random product of matrices. It's not straightforward. There is a lot of work to adapt that argument to this setting. But I want to point these 2 that are the things that give that give a problem when you go to the partial hyperbolic setting. So the first one I'm going to call pinching. That is the following. When I'm in this setting, my base is an OSOP. I'm with a linear cocycle of dimension 2, and I have different Lyapunov exponent. I can guarantee that there exists a periodic point such that when I look to the linear cocycle at this point, here is the period of my point, then this map has 2 different eigenvalues. This is a consequence of the result of Kalinin. So in this setting, if I have different Lyapunov exponent, then I'm able to find a periodic point that has this property. And this property is open. If I perturb my linear cocycle, I'm still going to have this property. So here you see that we already have a problem, because if my base is partially hyperbolic, this here is not necessarily existing. I can't have a partial hyperbolic without periodic points. So this is one of the major differences when I'm going to the partial hyperbolic setting. Today, I'm just going to focus in this one, but I want to mention this problem here that is very simply to explain, not formal, that is what I call local product structure. So in the setting of a no-sub map, you have this local product structure. You have unstable manifold and stable manifolds. And essentially, the idea is that you can project the stable manifold and restrict your problem here to the unstable, the black one here that is unstable manifold. So you have a projection that reduces your problem to the unstable manifold. And of course, this is not going to work in the partial hyperbolic setting because you have another direction. You have also a center direction. So this is not working, and it gives you a lot of problems. So this is much more delicate, so I'm going to focus today in the first one. What can we do to solve this first problem that appears here? So what we can expect is the following. I have my setting, and I have my conjecture that here everyone should be continuous. So maybe I'm not able to prove this, but I'm able to prove something that gives evidence that this is actually true. So I'm going to state two different conjectures that are partial answers to the first conjecture that appears to be simpler to solve. So the first one is about open and dense of continuity. So maybe I'm not able to prove that everyone is continuous, but I'm able to find an open and dense subset of this space B such that everyone there is a continuity point. That would be a first step. If I want to make sure that my conjecture is true, a first step can be to prove that there exists an open and dense subset of continuity points. A second situation that I need to address is this. If I have a map here that is approximated by C2 diffeos, such that the center Lyapunov exponent of this sequence here, of the perturbed one, are equal, then the center Lyapunov exponent of F should be equal. So let me rephrase this. What I'm saying is it cannot happen for my map to have different Lyapunov exponent and being approximated by maps that has equal Lyapunov exponent. That would be a problem for the continuity. If I'm going to find a map with different Lyapunov exponent that is approximated by diffeos with equal Lyapunov exponent, then I'm not going to have continuity at that point. So this should be happening for every map here. This one, I personally like to call Bocquet-Magne is not happening. So Bocquet-Magne is a result for surfaces, for maps, area preserving maps in surfaces, and said exactly that. Bocquet-Magne says that I can find maps with different Lyapunov exponent that are approximated in the C1 topology with maps that has equal Lyapunov exponent. So I want to prevent that. I want to prove that in my setting, Bocquet-Magne is not happening. So I have these two conjectures that gives good evidence of what happened here for the general conjecture.
Sorry, Karina, I have a question. In the conjecture one, you have this set U that is open and dense. You have in your conjecture, you have a description of this set. Is the set satisfying a list of properties or something like this? Or you don't think in that
No,
way?
that would be the perfect situation. But no, at first, no.
Okay.
I'm going to stay, the last theorem that I'm going to stay is going in that direction, and I'm going to tell you there what should be the condition.
Okay, thank you.
Okay, so the question is if this is actually something that we can prove for the center Lyapunov exponent. Of course, all these questions make sense in the case of linear cocycles. I stated here in the case of center Lyapunov exponent, but all of them have a counterpart when you ask the question about linear cocycles. So, as we already have seen, for linear cocycles over an of maps, here I have a problem. Okay. For linear cocycles over an of maps, we know that the general conjecture is true. And this is the result of Backus, Brown, and Butler. So here we do not need to worry. Of course, conjecture 1 and 2 are true because they are weaker than the general conjecture. But there is an intermediate step between linear cocycles over an of maps and the center derivative cocycles. And it's the case of linear cocycles over partial hyperbolic maps. So in this case, my base is partially hyperbolic, but I'm perturbing only the cocycle. And the general conjecture is still open. We don't know what happened here, but we have information about the two weaker conditions. We know that conjecture 1 and conjecture 2 in this setting of linear cocycles over partial hyperbolic maps are actually true. The first one is a consequence of results of Avila Santa Maria Viana and Avila Viana. This is not a state as conjecture 1 in their papers, but it's a straightforward consequence of the result that they state in these two papers. So for linear cocycles over partial hyperbolic maps, we know that we have a dense subset, an open and dense subset of continuity points. And in this case, we have a characterization. We can give a precise definition of which this set is. And it's going to have something to do with these SU loops that I'm going to define in a minute. I just want to mention that conjecture 2 is also true. We know that for linear cocycles over partial hyperbolic maps, Bocchi-Magnet is not happening, and this was proved by Backus, Poletti, and Sanchez. So we have this very good evidence for the conjecture, but it remains open, and we still don't know if we have continuity in the full set of fiber-bunched cocycles over partial hyperbolic maps. So why I have these SU loops here? Because of the following. I told you that in order to adapt the argument here, we have these two problems. Okay. We have these two problems here. We have this pinching problem and we have the local product structure. Both weaker conjecture 1 and conjecture 2, are possible to prove without using this local product extractor, but they need something like this pinching condition. So you have to deal with this problem in order to prove conjecture 1 and conjecture 2. And so the way that these papers deal with that problem is studying SU loops. So recall that I am in the partial hyperbolic setting and I'm asking for my partial hyperbolic map to be accessible. So I have SU path such that every part of the SU path is contained in a stable manifold or in the unstable manifold. So here, this is contained in the stable, unstable, and so forth. So I'm saying that I have an SU loop if the SU path starts and finishes in the same point. This is the fiber. Recall that for the projective cocycle, I have a circle. And since I have holonomies in every one of these, I can take the composition of these holonomies and I'm going to define a general holonomy that starts and finishes in the fiber over X. And what you need to do is you need to study these SU loops. I want to mention that this proof here of conjecture 1 and conjecture 2 in this setting is not a straightforward adaptation of the case in the anosov here. It's just not replacing this for periodic points. It's a very complicated argument where they need to deal with very many difficulties because you have your partial hyperbolic map in the base. But what I want to point out is this is a natural thing to appear here. If you recall Lipschitz theory or cohomology equation, you know that for a no-sub map, you put the condition in the periodic points. For partial hyperbolic maps, you put the condition in the SU loops. So it is natural that they appear here. Unfortunately, this is not something that you can adapt to the derivative cocycle. So recall that for the derivative cocycle, I'm perturbing the base. So I'm perturbing the stable and unstable manifolds. This is more likely that it's going to break. And these two proofs of conjecture 1 and 2 are dealing with estimation very precise of what happened in the base, because the base is fixed and they don't need to preoccupate for this. So the question is, what can we do in the general case? What can we do in the derivative cocycle case to understand something about conjecture 1 and conjecture 2? So let me state the theorem here. I'm going just to say in a minute what this means, and I'm going to give the precise reference for the theorem. But what I'm saying is I'm in my set B, and I'm going to impose an extra condition that I'm calling hypothesis 1, or I'm going to impose another condition that I'm going to call hypothesis B, 2, sorry. And I'm not able to prove the conjectures in the general setting, but I'm able to give a partial answer to the conjecture when I'm adding these two conditions here. So just to recall, the first conjecture asks for an open and dense subset of continuity points. The second one says that Bocchi-Magné does not happen. So what I'm proving here is not a general conjecture, but I'm saying that if I have this hypothesis here, I can approximate in the C2 topology by C2 open sets of continuity points. So it's a partial result of what I want. And the second one says that for this map with this hypothesis, Bocchi-Magné does not happen. So what are these conditions that are appearing here? I mentioned to you that the problem is this pinching condition. The problem is this periodic point that we have in the Anosov case, thanks to the result of Kalinin, and we need to make something here because in the partial hyperbolic map, that is not necessarily true. So the first easy thing to solve your problem is you ask for a periodic point. So hypothesis 1 is, besides all the hypotheses that I have in my set B, I'm going to ask for the existence of a periodic point. And as before, I want to have two different eigenvalues when I look into the cocycle at the point P. So this is exactly what was happening in Kalini. I have my linear cocycle here that has two different eigenvalues. So I'm not able to get this condition, so I'm going to ask for this condition in my hypothesis. But the good news is, in this case, I'm able to give a partial answer of the result. We are able to approximate this type of diffuse for open set of continuity points, and we are able to prove that Bocchi-Magné does not happen in this case. This is part of a joint work with Xiao Liang and Yagang Yang when we study this type of problem, adding the hypothesis of having the map F having a periodic point. And I want to address this extra hypothesis I'm putting here because I told you that I need this condition to be open. So in the Anosov case, I have the periodic point by Kalinin, and moreover, this condition was open. Now, even if I ask only the first one, this is not going to imply that I have an open condition. I'm going to perturb my diffie, and I want to have, again, a periodic point with the same properties. And that's why we need to ask this extra one here. So this is the first hypothesis to impose this periodic point that you need. The second one is in the same spirit that I was telling you before. My map F is going to be in my set B. Here I'm asking about dynamically coherence, and I'm going to talk about this in a minute, but the condition is imposed in SU loops. Sorry. So I'm not asking for existence of periodic point because probably my partial hyperbolic map does not have periodic points. As I told you before, it is natural to replace the condition in periodic points for condition in SU loops. And I'm imposing the condition of two different eigenvalues and being hyperbolic in the holonomy that is defined by the composition of the holonomies for the SU loop. So this is a joint work with Pablo Carrasco and Javier Correa. And what we prove is that with this condition, when I have my map F, we need to ask for dynamically coherent, but SU loops that are hyperbolic also provide a positive answer to a positive partial answer to the conjectures. So here, what I'm saying is I have a map with all these properties. I have dynamically coherence. I have an SU loop that is hyperbolic, and then I'm able to approximate it by open set of continuity points, and I'm able to guarantee that Bocchi-Magnet does not happen in this case. So this condition here, the dynamically coherence here, is important in order to guarantee that this condition is open. As before, I need to be able to prove that this condition is open, but I need to point out that this is a very much delicate argument because I'm dealing with SU loops. As before, I have an SU loop for S U path that starts and finish in the same point, and I'm going to perturb my diffie. And I need to guarantee that for every C2 open close diffie, I also have an SU loop. And this SU loop also have these properties. So just let me see here. I have my point X. I have the SU loop for F. And the problem is when I'm going to perturb, this is most likely going to open. So it's not very easy to get SU loop for the perturbed one. And you need that for the argument. So the fact that dynamically coherent is helping is because there is a relation between, I'm not going to give the precise definition of dynamically coherence. I'm just going to say that this implies that you have center leaves that are tangent to the center bundle. So there is a relation between the holonomies in the center leaves with this map here. And we are using that information in order to get that this is an open condition. We were hopeful to have this condition removed. We hope that phase foliation were sufficient to prove the argument, but at this point is everything rather technical, and we are still dealing with that case. So I don't know how much time I have.
I believe your time is ending right now. So 2 minutes or.
Okay. So I'm just going to stay here. I'm not going to tell nothing about it. It's this is a theorem that I want to present that I was not able to, that give information when your measure is not Lebesgue. So everything that I told you before is for accessible maps and ergodic, a Lebesgue measure. This is a more general result with a lot more of conditions that give some idea of what happens when you have another measure that is not Lebesgue. And this is part of the joint work with Xiaoliang and Zhang Zhang. So I'm stopping here. Thank you.
So thank you, Karina. Thank you, Karina. So are there any questions?
Could you show your condition on the existence of the loop?
Sorry?
You have this hypothesis where you have this loop. But my question is, when
Yes.
you have one loop like this, you have infinitely many, or you have a kind of I don't know how to say, density or something like this? Maybe.
We don't know. It's the natural question to ask, but we don't know yet what happened.
Okay. But you have no idea how these loops change when you perturb the dynamics. Of course, it's a very naive question.
No, what we can say is that for dynamically coherent, when the map F is dynamically coherent, I'm not asking for the perturbed one to be dynamically coherent, but when this one is dynamically coherent, we find an SU loop for the perturbed diffeo that is also has hyperbolic holonomy.
And this
But
new
we
loop,
can,
this new loop is close to the initial loop or something like
yes,
that?
yes. We found a new SU loop close to the original one. The point X is not going to remain. It's another point near this one that is closing, and the holonomies are close because I told you that the stables and stable foliations are close. And therefore, the holonomy is also hyperbolic for this new SU loop.
Okay. Thank you, Karina.
So, can I ask, can you give a precise, more detailed statement of your last theorem?
Yes, this one.
Yes.
Okay, so here, let me close here. Okay, so here I'm still with a partially hyperbolic map in the C2 topology with two-dimensional center bundle, and I'm asking for this Fibonacci condition. But what is important here is that I'm not asking for accessibility, and I'm not asking for the measure to be Lebesgue. This is for every ergodic measure. And what I'm taking is any sequence going to F in the C2 topology, and every sequence of measures going in the weak star topology to this original measure. I'm remarking here that I'm asking for this to be ergodic for the FK map. And if I put for F a condition that I'm calling bundle free, that is a condition that we expect to be the characterization of this open and dense subset where you have continuity, you need to have this property here that says that the partial entropy along stable or the partial entropy along unstable manifolds are continuous. If you have this, then you have the continuity of the Lyapunov exponent. And I think that a better way to express this, think that you have this measure being hyperbolic. Imagine that these center Lyapunov exponents are different from zero. Then in this hypothesis, you can guarantee that there exists K big enough that everything here is going to be hyperbolic also. So the idea is that in order to guarantee that the measure stops being hyperbolic, you need to break one of these. You need to collapse the entropy along a stable manifold, or you need to collapse the entropy along a stable manifold.
And are there, sorry, can you hear me?
Yes.
Can you, do you have some examples where this would be the case, or no? This is completely open, where you could break this,
You ask for this condition here?
no, for the convergence of the entropies.
Ah, this one. I don't know.
Okay, thank you.
Are there more questions?
I have one.
Yes.
Yes, Karina, in your last theorem, do you
Yes.
know, maybe it's a very simple question, but do you know what about the converse? Say that I have discontinuity. Do you necessarily have convergence of the two entropies?
I don't know. I'm not sure if I believe that that is the case. If I had to, I don't know. I think that probably not, but I'm not sure.
Maybe in some nice class like equilibrium states or something like that. Because say in an SRV, that, for example, if the measure will be the SRV, that should be true, right?
Yes, if the
Right.
measure is SRB, you have a relation here with the Lyapunov exponent. So.
Right. So then maybe for equilibrium states, that also is going to hold.
Yes.
Okay, sure. Maybe any measure will be too much to ask. Right. Thank you.
Yes.
More questions? If not, let's thank Karina again. And we should also take this opportunity to thank Lorenzo for organizing this series of seminars, since today is our last seminar of this semester. So let's thank Karina and Lorenzo.
Bravo.
Thank you.